Okay, so I'll now describe how you can derive Hamiltonian mechanics in terms of the Lagrangian. Okay, so again, as before, you're given the Lagrangian. L, which is a map from the tangent bundle, which has local coordinates q and q dot to the rails. Okay, and then so you can obtain from this, you can obtain a Hamiltonian denoted by H, which is a map from the cotangent bundle to the configuration manifold to the rails. And the local coordinates for this are usually of the form position P, position Q, and momentum P. Okay. All right. So so you have a Hamiltonian H, which depends on position Q and momentum P. Okay, and this is equal to Pi Q dot I, where I've used the sort of implicit sort of Einstein summation convention, right? Which basically says that if you have a repeated index, one of which is raised and one which is lowered, there is an implicit summation there. Okay, and then minus L Q dot. All right. So if you look at the right-hand side of this expression, you have P's, you have Q's. So you have P's, you have Q's, and you have Q dots, right? So, but on the left-hand side, you only have Q and P. So you basically have to have a prescription for what Q dot is in terms of Q and P. Okay, and the way you do this is you restrict yourself to the image of what is called the Legendre transform. So you require that P is equal to dl dq dot, okay, which is an expression which we saw before when we were describing Lagrangian mechanics and the Lagrange equations. Okay, so if the Lagrangian is what is called hyperregular, which more or less means that the associated Legendre transform is invertible globally, then you can use that to figure out what you can use this relationship to figure out what Q dot is in terms of Q and P. Okay, and then more generally speaking, if you don't have the invertibility of the Legendre transform, you can write the Hamiltonian as the extremum of the same quantity, Pi Qi dot minus L Q dot, but where you take extrema over sort of Q dot. Okay, and then it's easy to convince yourself that the stationarity condition for extremizing over Q dot is exactly the condition that P is equal to dl dq dot. Okay, all right. So anyway, so this gives you a Hamiltonian in terms of the Lagrangian. You can sort of play around with it and then sort of think of it as giving you an expression for the Lagrangian in terms of the Hamiltonian, and then maybe substituting that into Hamilton's principle. Okay, so so by using this to express the Lagrangian in terms of the Hamiltonian, right, you can modify Hamilton's principle to what is called Hamilton's phase space principle, right? So we obtain Hamilton's phase space principle, or Hamilton's principle in phase space. Okay. Okay, and it says that the variation of the integral, the action integral again, of Pi Qi dot, okay, minus H QP. Of course, this thing is essentially the Lagrangian, right? Dt is equal to 0, again with the condition that the variation of, well, I should specify the n times, right? T0 and T1, variation of Q at the n times vanishes. Okay, so these are the boundary conditions for the variations. So this is this condition that, again, the variation of this action integral expressed in terms of the Hamiltonian, right, subject to variations of Q which keep the endpoints fixed. Okay, that's what we call Hamilton's principle in phase space. So let's see what you get when you work with this. Okay, or maybe I should do this on sort of on a fresh slide. Okay, so let me just rewrite this at the top of this so that we have a bit more space. Right, so this is what is called Hamilton's principle in phase space. Right, which is that 0 is equal to the variation of the integral from t0 to t1 of pi qi dot minus h qp integrated over t. All right, let's see what you get when you compute this variation of the action integral expressed in terms of the Hamiltonian. Okay, so again, it's like you do this usual trick where you swap the integral. It's like and the variation. It's like, and again, because of the fact that the variations vanish at the endpoints, the boundary terms which would normally be associated that would vanish. So you just get the integral from t0 to t1 of so I first differentiate the p term, right? So I get a variation of pi paired with qi dot, right? Plus I leave the pi and I take the variation of qi dot, right? And so this gives me the variation of qi dot. And then I have to again apply the chain rule. It's like to obtain the variation of the Hamiltonian. So I get a dh dq term and then variation of q. And I'm just going to put all the sort of the indices there, right? Minus dh dp variation of pi. Okay. Okay. So by convention, it's like the indices on position, it's like are raised, and the indices on momentum are lowered. And that has to do with the fact that position is essentially like a vector, and then, or described in terms of a vector, and then momentum is described in terms of what is called a covector. And so these things transform differently under change of coordinates, and the raised and lower indices sort of remind you of that, right? Okay, so so we'll talk a little bit more about what this all means. It's like in a little bit, but for now, it's like just be mindful of the fact that positions and momentum transform differently under changes of coordinates. Okay, so let's see what happens. So as was the case with the usual Hamilton's principle, what you want to do now is you would like to write down everything just in terms of sort of independent variations. So the momentum variations are independent from the position variations, but the velocity variations and the position variations are related to each other because the velocity is the time derivative of the position. So as before, you want to do an integration by parts. It's like on this term involving the variation of the velocity, okay, because you want to think of this as the time derivative of the variation of the position, and then do an integration by parts on that piece. So when you do that, right, you get the integral from t0 to t1. So I'm going to put all the variations at the end now. So it's q I dot variation of pi minus sort of d dt pi variation of qi, right, minus dh dqi variation of qi, and then minus dh dpi variation of pi, and then dt. Then there's a boundary term which is pi variation of qi, evaluated at the limits t0 and t1, and of course this vanishes because of the endpoints being fixed in the variations. So you're just now left with variations in p and variations in q, so we can start collecting terms. Okay, so you get something which says qi dot minus dh d pi paired with the variation in pi plus minus pi dot minus dh d qi paired with the variations in qi. And then when you integrate this over t, it's like these things are 0. Okay, so again, by the fundamental theorem of the calculus of variations, these things, it's like which are paired with the variations, have to vanish because the variations in P are independent of the variations in Q. So in order for this to be equals to 0, it's like for all possible variations in Q and P, it has to be that these things inside these curved brackets have to individually vanish, right? So by the fundamental theorem of the calculus of variations, right, we obtain the condition that so q dot I is equal to dh d pi, and then pi dot is equal to minus dh d qi. Okay, so these are called Hamilton's equations. And in particular, it's called Hamilton's canonical equations because, as we'll see later, this is related to a Hamiltonian system which has a canonical symplectic structure, so or canonical Poisson structure, right? Correct. Okay. So, yep, so that's it for now. We'll see how we can go from there.